Okay, so converging lens. That is the lens that you use in magnifying glass as a magnifying glass, or people who are farsighted use it as well to correct their vision. Focal point for this type of lens is real because your light rays actually do focus. And as you see, if you remember, a concave mirror also focused light rays. But if this was a mirror and that's where the light rays came from, that's where the focal point would be, and they would focus in the real world. The purpose of the lens is to let the light go through it and then focus it on the other side, because technically, if your object is here, your eye is behind the lens, so that's where you need to form your real image, or a screen for that matter. If you're, for example, if it's a projector, here's your, say you're showing slides, here's your slide, here's the projector's lens, and here's your screen right there. Or here's the object, here's the lens in the camera, that's where the image is formed. So there you go. The way to draw the image, it's exactly the same as a concave mirror. So what you're going to do, you're going to do one that is parallel, and you need to extend it all the way to the middle of the lens, and then it's going to go through the focal point. If it came through the focal point, it's going to go parallel. The place where they meet, you're going to have your tip of the arrow. So as you see, it's flipped, so therefore it's a real image, and it's smaller, exactly like with a concave mirror. Now, if you remember from the concave mirror, as I start getting closer to the focal point, my image is still going to be real, but it's just going to grow in size. And then once you pass the focal point, you should get a virtual image, but it should be bigger, and that is how magnifying glass is used. You hold it real close to the object and you see it bigger. So in this case, again, since you're far away from the lens, you get a real inverted and smaller image. I tried to draw, and we did in class, an image for something like this, but it's going to be heck out there, so I'm not just going to do that. I'm going to use my own. Here's my own object. It's between focal point and the lens, so it's closer than the focal length. And I'm going to use the parallel light, which will go through the focal point. And instead of going through the focal point and the tip, I'm just going to go through the mid-center. Through the center, I guess. There's no other mid-center, like mid-center, not mid. Anyway, so through the center of the lens. And as you see, these two guys that are the refracted light rays will not cross in real life. So your brain is going to extend one of them and find where they cross, and that's where your image is formed. Since it's upright and not flipped, that tells you that it's a virtual one, and in size it's bigger. The same kind of table that worked for a concave mirror will work for a converging lens. It gives you two types of images. It can give you a real image and it can give you a virtual. Virtual is when you use it as a magnifying glass. A real is when you're using a projector. Let's look at an example. So you look at a 45 centimeter object and you see it as a 15 centimeter object, so it's smaller. For this type of lens, that's a dead giveaway. If it's a smaller image, then it's real. So therefore it's going to be flipped. So the image height is actually negative 15 centimeters. So we need to figure out the distance to the object in this example. So magnification, negative 15 over 45. That's the height of the image, and it's flipped because it's real. 45 is the actual object, so it's negative 1 over 3. Negative di over dou equals negative 1 over 3. I substitute di because I'm looking for dou anyway. So di is going to be do over 3. I put it in the focal length equation. So 1 over dou plus 3 over dou, since I flipped it, equal 1 over f. F is 10 centimeters, so it's 4 over dou. Therefore, dou is 40 centimeters. That is when you get a real image. And the distance to the object is technically always positive. It's the di that can be negative. Now we're going to go for another example. So you use this lens as a magnifying glass. So you are getting a virtual image, which is huge. And it's upright. So therefore your height of the object is 1. But height of the image is not negative, but positive, 5, which gives you a magnification of 5. Then you're going to use di over dou. I'm looking for distance to the image because I'm asked to find how far from the lens is the image. So negative di over dou equals 5. Substitute di for dou, or you can do dou for di, whatever. I'm going to go di for dou because it's easier just to multiply these two guys. And remember, it's negative. So then 1 over f equals blah, blah, blah. So I've substituted die for dou. Then you use common denominator, which is 5 dou. So this is going to be 5 over 5 dou minus 1 over 5 dou. That's 4 over 5 dou. So then cross multiply, dou comes up to be 8. And then, since I'm looking for die, all I need to do is just multiply by -5, and that's negative 40 centimeters. So it's a virtual image 40 centimeters away from the actual object, and there you go.